So now you might ask the question, what exactly are you allowed to do to this augmented matrix that you start with, right? If you have a linear system and you want to solve it and you write down the augmented matrix, what are the rules? What are we allowed to do? And to answer that question, the answer is you can perform any of the following elementary row operations, and that's what we're about to talk about momentarily here. So it all boils down to three different actions that you can take. The first thing you can do, which is probably the simplest thing you could do, is you could interchange any two rows you like. Okay, an example of that, we did that at the very end. Okay, we did that here. When we were at this stage, we decided we were going to interchange the second and the third row. And I mean, it makes sense, right? Because it makes sense that that wouldn't change the underlying solution set, because it would be just like writing down the same equations, but just in a different order. So there's certainly, there shouldn't be any surprise that this doesn't change the solution set to the underlying linear system. The other thing you can do, the next thing you can do, these are kind of in order of complexity. The next thing you do is you can multiply any row by a non-zero constant. Okay, we actually didn't do that yet at any point in this last example, right? But let's say, for example, let's say at this stage, for whatever reason, let's say I wanted to multiply the entire row by 2. Well, then instead of having 1, 1, 2, 9, it would turn into 2, 2, 4, 18. So that's another thing you can do. You can multiply any row by any non-zero constant. And it's important that we multiply it by a non-zero constant, because if you multiply it by 0, well, then you're just going to end up with a row of zeros, and you're going to basically just lose any information that that equation gave you in the first place. So you can multiply any row by a constant, but just make sure that constant's not 0. We'll see examples of that operation being done in the future calculations that we do. Another thing you can do, and we did plenty of this, is that you can either add or subtract a row from another row any number of times. Or more specifically, this is the way to state it. You can add any multiple of any row to any other row. And by allowing for general multiples, we're allowing for negative multiples as well. So that explains why you're allowed to do subtraction. So some examples of when we did this would be going back to this example. Here's two examples where we added multiples of one row to another. In the first operation, we added -1 row 3 to row 1. And then in the second operation, we added -2 row 3 to row 2. We phrased it in terms of subtraction, but really we were just adding negative multiples. Another example would be down here. We added row 2 to row 3, but we did it 4 times. So we added a multiple of row 2 to row 3. So those are the three things you can do. And any row operations that you do had better boil down to those row operations, or you're doing something illegal, and in which case you might be actually changing the solution set without realizing it, and that will lead you to incorrect results. So any row operations you do must be from this list. And there's a comment that I added down here. It says, unless there's absolutely no risk of confusion, you should only be doing one operation at a time. So if you look back up, again, I'm going to go back to the previous example. A lot of these steps, I did several operations at once because there was no room for confusion. And here's what I mean by that. Notice in the very first step, I added a multiple of row 1 to both row 2 and row 3. There was no room for confusion. There was no potential conflict. So for what I mean by that is here, when this operation was performed, the only row that changes was row 2. Notice that row 2 is not involved in the other row operation that I perform. And that's what I mean by there's no room for confusion. So that's what you got to watch out for. You don't want to, like, let's say, for example, if you were to add row 1 to row 2, and then add row 2 to row 3, and then interchange rows 1 and 3, you wouldn't want to do that all in the same step. That would just lead to confusion and incomprehensibility. No one will be able to follow what you're doing. So if there's any potential confusion, just do the operations one at a time. And if you're not sure, then just do them one at a time anyway. And then as you build more confidence, you'll start to get a sense for what can be done simultaneously. But for now, just do your row operations one at a time. And remember, it always comes down to the fact that it always takes a lot longer. If you have to go back and start over because you've made an error somewhere, you'll wish you went slower and did it right the first time, because it takes a long time to find errors. And then once you find them, you still have to fix them. So anything you can do to reduce the chance of errors should be embraced. Okay, and just a couple pieces of terminology here. Some linear systems, as we'll see in a moment, don't have any solutions at all. And in that case, they're said to be inconsistent. But if they do have a solution, in other words, if their solution set is non-empty, it means there's at least one solution to the system, then we say that the linear system is consistent. And any linear system that's not consistent is said to be inconsistent, which again, I know I'm repeating myself here, but it's not so bad to hear the same idea twice. If a system's inconsistent, that means it has no solutions at all. So we've looked at two, well, I guess technically four examples if you include the ones we didn't solve. All of the examples we've seen so far have been consistent. But let's take a look at what might happen when you look at an inconsistent system.